Hello everyone, Human Hard Drive here. Today on Electronics 201, we're going to be talking about the digital applications of op-amps. A while ago we did a video, Electronics 101, the analog applications of op-amps, specifically using op-amps as amplifiers, pretty much what they were made to do. But today we're going to be talking about the digital applications because there are quite a few digital applications. Now, the first of which I talked about in the analog video, and that was to explain how amplifiers actually, or how op-amps acted as amplifiers. And that was the concept of the comparator. That is what an op-amp is, essentially. You've got an op-amp, and you've got the non-inverting input, and then the inverting input, and then you've got the output. And you've got the two leads. Remember that I'll call this V minus V in minus V in plus, so that it doesn't get confused later. I'll add those now: V minus and V plus. Okay. So remember I said we'll call this V out. Keep making addendums. Remember I said if V in plus is greater than V in minus, V out is V plus. And if V in minus is greater than V in plus, V out is V negative. And I'll add one more case. I don't think I mentioned, or I brought this one up. If V in plus is equal to V in minus, V out equals 0. This is the basic application of an op-amp. An op-amp is a differential amplifier. It amplifies the difference between the two inputs. So what happens is, because one input is greater than the other, say Vn is greater than Vn plus is greater than Vn minus, it's going to amplify all the way to the max voltage it can supply, V plus. Now remember, with the amplifier, there was some feedback loop to make sure that V out didn't grow all the way to V plus. With a comparator, you want it to go all the way to V plus. However, you're going to usually keep that to a smaller voltage, say 5 volts as opposed to 15 or 25, whatever your max amplifying voltage would be. This is more used, remember, this is used in digital applications. So, what would this be used for? Well, we'll start with that. What would this be used for? Let's say you want to monitor the voltage of something, and you don't have an analog to digital comparator, or you want to save an analog to digital comparator. You can use this to test. Say you have a battery, and you're trying to monitor that battery. So let's say this is a 9-volt battery, and this is obviously separate from your power supply, whatever you're powering the op-amp with. What you can do is you can connect that to the non-inverting input of the comparator, and then you can connect the inverting input to a voltage divider. That's a potentiometer, very poorly drawn. Let's see if I can do that a little better. Connect this to a potentiometer. I guess that's as good as I'm going to get. We'll call this, I guess, 5 volts. Now we'll make this, say, V plus. And we'll make this ground, and I'll make this ground. And then this is the output. Okay. And we'll make this go to 5 volts. And this go to ground as well. Okay, that's kind of a very poorly drawn. But with this, what you can say is, if this battery drops below a certain voltage, and you can control that voltage with this potentiometer, it will generate out a different signal. So as long as the 9-volt supply is greater than whatever this cutoff voltage is here, the output will be 5 volts. The second it drops to below this voltage here, output becomes low, goes to ground, and something happens. You're now aware that it has dropped. So this is a very simple way to make a battery voltage detector. Obviously, there's a better way to make a battery voltage detector, but this is a very simple one. This also works with current measuring devices, current measuring devices will output, instead of a current, will output a voltage, and then you can compare that voltage to something. And then that's where a comparator comes in. Now, let's talk about the difference between a comparator and an op-amp. Obviously, you can make an op-amp into a comparator. You just don't have a feedback loop. That's good in a pinch. However, a comparator will have a much higher response rate than a normal op-amp, meaning when you change the voltages on Vin plus and Vin minus, it's going to be able to respond a lot more quickly because you don't have to keep up with the feedback loop and you don't have to worry about oscillation a lot of times. So again, comparators are a lot faster than op-amps. You will be able to buy devices that are comparators and devices that are op-amps. So that's the big difference between an op-amp and a comparator. A comparator will not generally work as an amplifier. You shouldn't try to make it run as an amplifier, but yeah, well, just don't. So those are the differences between a comparator and an op-amp. Now, that is one application of an op-amp in a digital environment. The second one we're going to be talking about, move to a new page, is something called a Schmitt Trigger. Now, before I talk about what a Schmitt Trigger is, I'm going to have to insert a little knowledge here, a little piece of information that will help you understand what's going on here. That little piece of knowledge is the concept of hysteresis, and I have that written down so I know I spell it correctly. Hysteresis, specifically a hysteresis loop. Hysteresis is, and this is according to the Wikipedia definition, the dependence of a system not only on its current environment, but also on its past environment. What does that mean? Well, a Schmitt trigger is like a comparator, except it has a difference. A hysteresis loop is something that looks like this, and you'll see this symbol used on the Schmitt trigger because it relies heavily on the concept of a hysteresis loop. Basically, what that definition says is, in order for it to change, it has to be at a current state. So, in the case of a Schmitt trigger, in order for a change to occur, in order for it to go from low to high, it already has to, from low to high, it already has to be low, and in order for it to go from high to low, it already has to be high. Let's take a look at what that actually means. So let's draw a graph, and you know me, my graphs are generally stellar, especially when I'm on my lovely tablet here. And we'll call this, actually, we'll call this V, and this is V prime. And let's draw a weird wave thing. There we go. Now, a comparator has one reference voltage, be that the non-inverting or the inverting input, depending on whichever one you want. It's not important. It has one reference voltage. And we're going to draw that reference voltage right about here. You know what? Because I'm employing technology, I'm going to use a different color ink. Yeah, look at that. Okay. Oh, scrolling a little too far there. Okay, so what does this cause? Well, if we were to draw another graph, again, stellar graph by me, V prime, this is going to be the output. Because I'm going to have to draw another one of these, I'll copy this now. There we go. Okay. So this is going to be the output of a comparator. So we'll call this Vin plus, and we'll call the waveform Vin minus, just for the sake of a comparator. So right about to here, and this is going to be tedious, but I will do my best. It is below the reference voltage, so it's going to be, I'll use red again, it's going to be low. Then, till about here, it becomes high. Then again, it goes low. Really showing my art skills here. Then it goes high for quite a long time. Come on, give me some dotted lines. There we go, and then it goes low again. Okay. So with only one reference voltage, you're seeing a lot of variation. It's jumping up and down a lot. What a Schmitt trigger does, remember the hysteresis loop, it has to be low first in order for it to go from low to high, and it has to be high first in order for it to go from high to low. What that introduces is the concept of two reference voltages. So I'm going to have a higher reference voltage, and I'm going to have a lower reference voltage. Now, depending on the kind of Schmitt trigger you have, inverting or non-inverting, it's going to change a couple things. There's my cursor. I keep losing it. What that's going to change is how it's going to respond. Basically, it's going to be like on a comparator. If this, instead of Vn plus the non-inverting input, it was the Vn minus the inverting input. So that would just invert the graph I'm about to draw. Or rather, not draw, because I had the foresight to paste it, or copy it. Now I'm pasting it. Oh, okay, V prime. Apparently I'm still using blue ink. Okay. So, I guess I'm going to try and use the same dotted lines I drew above to mark this. And I'm going to try and do this rather quickly, which, as we all know, increases one's accuracy immensely. Okay, so now we're going to use blue. So we'll say it starts at ground. I foolishly put this lower line. I should have moved this lower line up a bit, but so that you could see the change better and ignore the starting state. But generally, the starting state, because we're using a bipolar supply, would start at 0. Remember, a bipolar supply goes from a positive voltage, say positive 12 volts, to negative 12 volts, not 0 to 5 volts. That's a unipolar supply. So normally it would start at 0. So we can see, we'll assume it starts low, just for the sake of simplicity. And it doesn't actually, oh, I shouldn't have drawn those dotted lines. That was a bit dim of me. I apologize. Just undo that. Too far. There we go. Okay. So now we're going to have to try and remember where this line is. So we'll assume it starts low. So it only goes high here at this point. So if it's right about there. I think we can all remember where that is. Yeah, right about there. And it only goes low, or below this state, here. So a little after that last dotted line. Yeah, stellar line there. There we go. So as you can see, and again, this is very poorly drawn, but I have a better example in in a little bit. As you can see, this removes a lot of variability from the graph. You've gone from an inverter, or getting ahead of myself. You've gone from having a comparator output to a Schmitt trigger output, which has two reference voltages. Remember, with the hysteresis, it's only going to change from one state to the other depending on its past state. Remember that definition? Dependence of a system not only on its current environment, the relation of the graph to this line, but also its past environment, whether it was already at a high state or a low state. Hysteresis works wonders. Okay, so I have in the wings Falstad's circuit simulator with, there we go, with Schmitt trigger here using an OpAmp. This is an inverting op-amp, and this is using a, if I remember correctly, a bipolar supply, in this case 5 volts to negative 5 volts. So here we can see the input voltage. As you can see, it's a really crazy waveform. And what I'm actually going to do is I'm going to copy this, or actually I'm not going to copy the whole thing, I'm just going to copy this bit. There we go. So now I've got that over there. And I'm going to plug this into a comparator. And I'm going to set the reference voltage to, where's the voltage source? There we go. I guess to 5 volts, that's fine. And we'll look at the output. Okay. And I'm going to remove this. Okay, so here we see the input. That's this crazy wave thing generated here. So as you can see, it's a sine wave, but with a whole bunch of, with a higher frequency sine wave added on top of it. So it adds a lot of variation. As you can see in the comparator output, very good, zoom in, or I try to zoom in, you can see that on the edges of where it changes state, of where it goes to below 5 volts, there's a spike up and down because of this jitter here. Because it's moving within a very fine band. It's moving quickly above and then back below the 5 volt line, and that's creating this jitter here. What we see here is almost exactly the same thing. So I'm going to guess that I tweaked with this incorrectly. What am I doing? There we go. Yeah, that was my fault. Okay. So as you can see, get my mouth working again. As you can see, the output from the Schmitt trigger here reduces that jitter quite a bit. And what we see here is that hysteresis loop. This is the symbol that identifies a Schmitt trigger. You'll see this on the label on schematics, indicating this is a Schmitt trigger. So as you can see, it's moving about like this because it's depending on the state it's currently at, either above or below that reference voltage, and where it's been, whether it's already at the high or low state. Now, what is a Schmitt trigger useful for? You can get Schmitt trigger inverters. So an inverter, if you know your digital logic, if you put in a high signal, you get a low signal out, and if you put in a low signal, you get a high signal out. What a Schmitt trigger inverter will do is it will remove some of the noise from that normal inverter. It'll get rid of a jitter so that you have a little bit of window. Again, Schmitt trigger is very good at removing this sort of indecisiveness. It will get rid of some bouncing in a digital signal. The voltages for this, I do have a formula. Keep in mind that this formula comes or assumes a couple things. Where'd Falstad go? There we go. It assumes a couple things. The biggest thing it assumes is that this is a rail-to-rail op-amp, or a rail-to-rail comparator, meaning that it goes all the way to, the output goes all the way to the positive voltage and all the way to the negative voltage, and the swing from both directions is the same. So, meaning that the distance from 15 volts to ground is the same as negative 15 volts to ground, 15 volts. So that formula I have, go back to my boring black ink. If you use the schematic I just showed you, and I'll go back to full screen, you have Vref. You've got a resistor, and that goes into the OpAmp, the inverting input. This is your output. That's what generated that hysteresis loop. V out, right? V out. That connects to another resistor, which connects here. which then connects to one more resistor, which goes to ground. And then this is your... Oh, that doesn't actually connect. Misread my own handwriting there. Put a loop here. There we go. That doesn't connect there, does it? See, now I've got to check. Falstad. Yeah, it doesn't. I've really got to learn to clean up my handwriting. There we go. Okay, so there we go. That doesn't. That's what that loop there means. And this is V in. This is R2, R1, and R3. And this is V minus. Oop, eraser. And V plus. Okay. Now the formula we have is, remember, assuming that actually I want to label those voltages so that I know what I'm saying. This is V ref, and this is V prime ref. You'll see it denoted as V and V prime. Okay, so what you get is V, can't even remember what I called it, V ref. I'm not going to call it V ref because V ref's already taken. I'll just call it V and V prime. Just remember that they're blue and different than this V prime. I apologize for that. V equals resistor 1, 2, 3. That's the sum of resistors 1, 2, and 3 over R2. You know, I'll write this differently. R1 plus R2 plus R3 over R2 times V ref plus R1 plus R2 plus R3 over R3 times VCC. What is VCC? Well, VCC is the it's the max. It's V plus. So I'll just rename this V plus. What is that line there? Appears sometimes, and I've got no idea what causes it. Okay, moving on. V minus, or not V minus, V prime equals R1 plus R2 plus R3 over R2 V ref minus R1 plus R2 plus R. Why do I keep writing B? R3 over R3 times V plus. And there we go. So that gives you the upper and lower bounds of that Schmitt trigger. So this is if you want to build a Schmitt trigger from an OpAmp. Remember, this is, I'll write, this is an inverting Schmitt trigger. 2 T's. The whole name Schmitt trigger has 3. That's quite a few T's. Okay, so that's how you build an inverting Schmitt trigger from an OpAmp. So again, Schmitt trigger, good at removing that jitter from an input signal. So it's good at debouncing, say, a digital signal or even an analog signal, as we saw with Falstad. And you've got the comparator. Simpler Schmitt trigger, but good if you only want to compare against one voltage. So again, like a battery comparator or a current detector will output a voltage that you can use to compare something to. And then that's what you have. So yeah, that's the digital applications of an OpAmp. I'm Human Hard Drive. Thanks for watching.